Welcome everybody, I'm Ádám Magyar, I'm a full stack developer at Benny Studio. I'm going to do the first part of this workshop. I'm going to try to explain quantum computing from a theoretical point of view to you. And in the second part, Gábor will take it and he will help you to explain a bit more in coding. And let me get started. So first of all, let's discuss what is a quantum computer. Quantum computer is a type of computer which is based on quantum mechanics. So it can perform certain kind of computations more efficiently than a classical computer can. Let me tell you the brief history of quantum computing. So everything started at 1900 with Max Planck's quantum hypothesis. He was a German physicist. He introduced the concept of quantized energy levels to explain the phenomenon of black body radiation. He proposed that energy is not emitted continuously, but in discrete packets called quanta. Planck's quantum hypothesis marked the beginning of a new era in physics and set the stage for the development of quantum mechanics. 35 years later, Albert Einstein, Boris Podolsky, and Nathan Rosen published a paper introducing paradox. This is called ERP paradox, which questioned the completeness of quantum mechanics due to the phenomenon entanglement. Later on, in 1964, physicist John Bell formulated his inequalities, which provided a way to test the validity of this ERP paradox. The violation of Bell inequalities in subsequent experiments confirmed the existence of entanglement, and this entanglement is a key resource for quantum computing. In 1970s, techniques for manipulating single atom quantum states, such as atom trap and scanning tunneling microscope, began to be developed. And it make it possible to isolate single atoms and arrange them in arrays. In 1980, the first conference of physics and computation has been made, which was a significant milestone in this field. It brought together physicists and computer scientists and mathematicians to discuss the potential applications of quantum mechanics. And 1 year later, Richard Feynman delivered a seminar lecture at this conference, proposing that a computer operating on quantum principles could efficiently simulate quantum systems. And in 1982, Paul Benioff, a physicist, published a paper describing a quantum mechanical model of a Turing machine. This model, known as a quantum Turing machine, laid the groundwork for quantum computing models by demonstrating that quantum mechanical principles. Yes, and later on in 1990, there was a significant progress in development of quantum algorithms. These years, in 1994, Peter Shor's algorithm was developed. Also, Grover published another algorithm this year, and these algorithms showcase the potential power of quantum computing, driving the investment in the field. And in the early 21st century, an intense race started. Researchers, tech giants, and startups started a race to build quantum computers. This period saw significant progress in this field, and as probably the main major milestone was in 2019 when Google announced that they achieved the quantum supremacy. They built a quantum computer with 53 qubits, and they told to the world that they run an algorithm on this computer which is solved a specific problem in 200 seconds, with which problem would be possible to solve with a classical computer would take 10,000 years. So you can see that it's a big difference. And this achievement marked the first time that a quantum computer outperformed classical computers. And since then, the development of quantum computers ongoing. There are a lot of challenges around quantum computing, and today we are able to run algorithms on quantum simulators, and also we can run quantum algorithms on the cloud as well. Amazon provides an SDK and virtual quantum computers for this purpose. Now let me compare quantum computers to classical computers to explain the differences and the main things. So let's start about how a classical computer stores the information. As you may know, that classical computers store information in bits, which could be either 0 or 1. And with bits, we can represent different kinds of informations like text, images, and so on. And what about quantum computers? They are not using bits. They are using something called quantum bits, which are working different way. That these qubits cannot be only set to 0 or 1, but it can be also set to 0 and 1. So they could be in superposition of 1 and 0. Regarding quantum computing, there are 3 important definitions what we need to understand. But the first one is superposition, the second one is entanglement, and the third one is interference. I'm going to explain this. Here is a bit about bits versus qubits. I hope it's visible. And let me explain superposition to you. So you can imagine superposition, like if you have a magical coin, which could be both heads and tails at the same time. In a quantum world, particles like electrons can be in multiple states simultaneously, like a mix-up of up and down. This is called superposition. You can also think about a qubit like a talented acrobat who can balance on multiple tightropes at once, showing off its flexibility and defying the rule of regular physics. We can also think about this quantum state and superposition like in the image. So I think most of you heard about Schrödinger cats. In this image, this superposition is illustrated like a cat which is inside a box with a bottle of poison. And the question is that is the cat is alive or dead, but from this point of view, the cat could be both alive and dead at the same time, so we can think about this way. Moving on to the second important definition, which is entanglement. So it can be explained that way, that you can think about your two best friends who can finish each other sentences no matter how far apart they are. In the quantum realm, particles can be entangled so that the state of one instantly affects the state of the other, no matter how far apart they are. This connection is so spooky that Einstein called it spooky action at a distance. So let's say that you have two entangled qubits. If the state of the one qubit changes, the other qubit will immediately change its state to match, even if they are galaxies apart. It's like they are sharing a secret language that breaks all barriers. You can also think about entanglement like having a pair of synchronized dancers who always mirror each other's moves, even on opposite sides of the stage. In summary, superposition allows qubits to be in multiple states at once, like a coin flipping in the air, and entanglement creates a mysterious connection between particles and lets them communicate instantly, no matter the distance. These two mind-bending concepts are the quantum magic that powers quantum computing's potential for super fast calculations and problem solving. And the third important definition is the interference. Interference happens when two or more waves met. Their highs and lows can build on one another, called constructive interference, or cancel each other out, called destructive interference in the quantum world, because particles behave like waves. Quantum interference comes into play. Constructive interference increases the probability of certain things, such as finding the particle in certain location, while destructive interference reduces that probability. And let me describe a bit about quantum circuit diagrams. So for classical computers, we also can draw this kind of diagrams. This is the same for quantum circuits as well. They are providing a visual representation of quantum circuits and a simple framework for comprehending and creating quantum computations. These diagrams uses symbols and lines to represent quantum information flow over a circuit, just like their classical counterparts. On the circuit diagrams, qubits are displayed with horizontal lines. They can be found in the quantum circuits, and each one is representing a qubit. And these lines trace the evolution of the quantum bits as they move through the circuit. In the quantum diagrams and in the quantum computing also we can use gate for operations, and there are a few of them which I'm going to explain. Probably one of the most important is the C-NAT gate. It's called the controlled NAT gate, which acts on 2 qubits. First one is the control qubit, and the second one is the target qubit. If the control qubit is in state 1, it applies an X gate to the target qubit. Otherwise, it does nothing. This gate is crucial for creating entanglement, a key resource in quantum computing. This gate also can be, we can also think about like a reversible XOR gate. The second important gate is the Hadamard gate. It's also a crucial one. It puts a qubit into superposition states. When we apply Hadamard gate to a qubit, which is in state 0, it transforms it to 0 plus 1 divided by power of n superposition, making it equally likely to be measured as 0 or 1. The use of quantum circuits to perform quantum computations become essential instruments in the quest for quantum capacity beyond the constraints of classical theory. The potential of quantum computing is centered on these circuits, which are made up of qubits and quantum gates. These circuits can perform complicated computations at an unparalleled speed by taking the advantage from classical computing. I brought a simple example to understand how quantum computers work. So let's suppose that you are running a travel agency and you need to move a group of people from one location to another. To keep this simple, let's say that you need only 3 people for now. Let's name them Alice, Becky, and Chris, or ABC. And we can suppose that we booked 2 taxis for this purpose, and we want to figure out that who gets into which taxi. And also we can suppose that we got the information about who's friends with who and who's enemies with who. And let's say that A and B are friends, A and C are enemies, and B and C are also enemies. And our goal is to maximize the friends pair sharing the same car and minimize the enemy pairs who are sharing the same car. So this is the basic premise of this problem. Let's first think about how we would solve this problem with a classical computer. So first of all, we need to figure out how do we want to store the relevant information with bits. We can label the two taxis with taxi number 1 and taxi number 0. Then we can represent who gets into which car with 3 bits. The second most popular quantum computers using photons, particles of light, to carry and process quantum information. And there's some nuance and complexity how it works. For large-scale quantum computers, it can be useful, and it's a promising alternative. And the third most widely used quantum computer is the neural atoms quantum computer. These are based on neural atoms. It involves atoms suspended in an ultra-high vacuum by arrays of tightly focused laser beams called optical tweezers. These kind of quantum computers are less sensitive to stray electric fields, which makes them a good option to. It is also used by a lot of companies, Pascal, atom computing, cold quanta, and so on. And the question comes that what does the future of quantum computing, what opportunities does it have? First of all, with the future of quantum computing, there would be improved hardwares. I mean, improved quantum computers, because nowadays, in order to, there are researchers working on to mitigate the effects of noise and decoherence, and they are developing better quantum computers, improving the error correction techniques. It also has a future in applications in chemistry and in material science. With quantum computers, we would be able to simulate complex chemical reactions and interactions that are difficult or impossible to do with classical computers. Quantum computers may be able to accelerate the discovery of new materials. The third important thing about quantum computing, and a lot of people is fearing of their bank accounts and so on, is the cryptography. It could potentially break many encryption algorithms, which are used to store secure, sensitive information today. However, the researchers also working on developing quantum-safe encryption methods that would be resistant to these kind of attacks. It also have a future with machine learning. With quantum computing, we would be able to solve optimization problems that are interactable for classical computers, such as those encountered in logistics and supply chain management. With quantum machine learning, it could also offer significant improvements in data analysis and pattern recognition. And last but not least is the hybrid classical quantum computing, which would look like a computer which is a classical and a quantum computer at the same time, but it uses the classical part for simple algorithms and using the quantum part of this computer for running the quantum algorithms to take the advantage of it. Overall, the future of quantum computing is bright, with the potential of revolutionizing fields ranging from medicine to finance to cybersecurity. Even so, quantum computing may not be widely accessible for several years. And let me talk a bit about hash functions, because in the second part we are aiming to reverse a hash. Let me do a quick intro to this. But before we get into the all the fancy stuff, I'm in the second part. Let me tell you what hashing is. To make it easy, let's imagine that we have a black box. And this black box is special. Let's call it a function box. And this box will map an independent variable on the input, dependent variable on the output. So let's say that our function box works like this. If we put a letter into the box, we get a number out of it. Since our box is a function box, there can only be one output for every input in the box. So let's say we are taking a letter from A to G on the input, and we map these letters to corresponding numbers from 0 to 9. So if we put a C inside, we will get 2 out of this box. This is the forms of this is the basics of how hash functions works. However, it in reality it takes a step further. It maps the data on the input to some numeric value on the output, usually in a hexadecimal sequence. So essentially, all hashing does is it uses a function to map data to a representative numeric or alphanumeric value. For the hash function, regardless of the size of the input, the output will always remain the same. There are 3 types of hash functions used mainly. First one is the cryptographic, used for instance, cybersecurity. Second one is the non-cryptographic, widely used for databases. And the third one is the fuzzy hash functions. They are also commonly used in data structures or computing systems. Hash tables comes into place when we are aiming to store these hashes in a data structure in an associative manner. In a hash table, data is stored in an array format where each data represents a hash, and all of them has its own unique index value. And this is useful because this way we are able to access the data very fast. With this data structure, we can use the advantage of insertion and search operations. These are becoming very fast, irrespective of the size of data. And let's take a 15 minutes break, and during that please clone the repository and install the requirements for the second part. And if you need help, please raise your hands, and me or Mate are going to help.
Hi everyone. Welcome to the second part of the workshop. At this second part, we will create some actual quantum circuits, and we will simulate them on your local computers, and hopefully at the end we can run them on real quantum computers. So if you get stuck, don't hesitate, just raise your hands, and my colleagues Ádám and Mate will help you. So let's see the repository you already downloaded, and hopefully install the requirements. We don't have too many requirements, just one, the Amazon Braket SDK, because we will use the cloud services of AWS Braket. This is a quantum computing service of AWS. Let's start coding in step 1. .py file from bracket.circuits. Let's import the circuit class. What's a circuit class? It's a representation of quantum circuit. So we create an instance of circuit. What can we do with a circuit? We can apply quantum gates. So we will run here a circuit with 6 qubits, indexing from 0. Then let's print this circuit. It will just print out the schema of the circuit itself. So you can see in the first line there is a T. It's a pseudo time concept of bracket. So you can see that at 0 timestamp it applies the identity gate to each of the 6 qubits. Now let's run this circuit. So to be able to run the circuit, we need to import a device. Let's import a local simulator, so it will simulate the circuit on your local computer, and say device is a local simulator. Then we create a quantum task, which is device.run, and it needs a circuit and shots. Shots means how many times this circuit will run. In first part, you saw that quantum circuits are not always deterministic, so you may want to run it several times to get out more measurements. And after running this task, we print task.result and check it out. So what's the result? Here we see, of course, the schema is the same. The result is a gate model quantum task result with lots of information for us. What's necessary is the measurements, which is a two-dimensional array. First dimension is a shot, so here we have one shot, one array, and the inside the measurements of these 5 qubits. Each of them are 0 because the simulations are starting with a qubit state of 0. Also, one handy tool here is the measurement counts. If you have more shots, let's say 1,000, this counter shows you that it's a key value pair where the key is the quantum result as a bit string, and the number, the value is the times, the count, how many times it appeared to be measured. Also, the measurement probabilities are similar, just it's not the count itself. Not the count itself, but the probability of the outcome. So, yeah. Let's go back to the slides and show you how I imagine this. So I imagine when I run this circuit, I imagine that these qubits are prepared like balls in the bowling center, and when I run them, I like throw them parallel to each other. At the end, there are some gates on the lanes, and at the end we measure. So that's how I explain it to myself, what happens here. Here are the results. There is a good documentation about the bracket SDK, so you can learn what are the measurements, measurement counts, if you are more interested. Okay, so let's go back to our code and apply another gate. Let's say the X gate. X is the negation, and let's say we negate 0, 2, 3. So at the end, we just need the measurements output. So you can see that the schema changed. Another timestamp, index 1, is here, and for indexes the 0, 2, and 3, the X gate appeared here. And the measurement is according to that 1, 0. Yeah, so in the presentation I put 3, 0, but it doesn't matter if we put 0, 3, then we see here that it's the 0 bit is 1, so it will flip the third qubit, so it will become 0 again. So the result is 1, 0, 1, 0, 0, 0. Let's do one more thing, which is necessary for our later job. Let's apply 4 CNOT gates. Let's do it for 0 and 4 and 0. Then apply 0, 2. Then apply 1, 3. And then apply 5, 1. Actually, the identity is necessary only if you doesn't maintain consequent. So if you have all of the qubit indexes later in any gate, you can leave it. If not, then the simulator will complain about that some qubit is missing. So here we see these CNOT gates. as you can see, there are only 2 timestamps because some part of that can be run parallel. But let's say this C0 02 can be run only after C0 40 because the 0 bit can't change. And let's say we apply or we check what if we apply an X for 0, 1. So we negate the first two qubits, and you see that the result is 1 1 1 0 0. Until now, you can see that there is the quantum circuit is deterministic. It doesn't have any random results, and we feel that these operations can be implemented in a normal computer. So yes, until now it's true. That's because we didn't put any qubit in superposition state, so they are either 1 or 0. Let's implement this chain of gates in a simple function. We call it hash. Now you know the purpose of this function, and if you want to mimic the quantum operations, then we need to agree that the message is 6 characters long, so mimic the 6 qubits, and we will say that the hash is the first 4 bytes after this, or qubits after this operation. So we implement inside this function helper C0 xy. So just we can write down in a nice way. X and y will be strings. So we create an integer from string, and we just apply the XOR operator. So this is the XOR operator, and we convert it back to a string. So this is our helper function. And what do we do with the message? We create a result, which is first we create a list of the message. It will be a list of characters, all of the characters, and we implement the same C0s like this. Result 0 equals C0. Result 0. Result 4. So the C0, the two indexes of the C0s are here, and since the control is the first one and second is the target, we should put the target here because we override the target but doesn't change the control. So let's do this operation for all these 4 C0s. I'm copying there on this line 4 times and then change the indexes. So the controls are the next one. The control is 0 and the target is 2. And the target is 2 here. The control is, but the first one is, it's good also like this, but to be consequent. The control one is the first one, so 4, 0, and now 0, 2, 1, 3. 1 is the control, 3 is the target. 3 is the target, and 5 is the control, 1 is the target. 1 is the target. And let's say we return a result, but only the first 4 bytes of it, and we create a string of it by joining them with an empty character. Okay, so we have this hash. Let's print out the hash itself, and let's mimic this 1100 0. So it should be 1111. So the hash should be 1111. Let's check out. Yeah, the hash is 1111. If we want to, if we want to check it out whether we implemented it the full of it correctly, the full sequence of qubits, then we can check it out. Okay, so we will need this hash function at the second part of the coding part. So up to now, these quantum gates seems to behave quite deterministic, and we don't see the superposition and the entanglement things which we heard about on the first part of the workshop. So let's leave the hash for now, and create a superposition state with a Hadamard gate. It's just a simple age, and of course you can apply the same indexes of qubits. If you run it, then you see that we have 6 qubits, all of them with a Hadamard gate, and the measurement seems to be random. If we increase the shots to, let's say, 10, we see more results. It seems to be kind of random. Let's check out here the slide. So the Hadamard gate, the 1 divided by square root 2 means that the probability of 0 and 1 will be 50%, because we need to square the coefficient to get the probability of the outcome. So this should be either 1 or 0, and it should be fully random. We see it seems to be random. Now I need to tell you that if it's running on a real quantum computer, it's a real random number, and it's quite a big thing, because we can't generate real random numbers in normal computers. What we generate usually is a pseudo-random number. It's generated with an algorithm which is very sensitive to the input arguments, called seed. And if this algorithm is broken, you can easily find some articles like this. It's from 2017, so you don't need to hurry and change your routers. But in 2017, one of the Wi-Fi protocol was compromised, because, as it turns out, the random numbers used on VPI WPA2 aren't quite random enough. So, as you can see, real random numbers are real issues, and generating them is it's not easy if they need to protect something like a cryptographic random number. And we get it easily by just Hadamard gate on a quantum computer. So yeah, that's nice. Let's check the second big thing, the entanglement. How can we do it? We apply one Ádám gate on index 0, and then we apply a CNOT gate. Control is 0, target is 1. Now we run it, and we see that 0, 0, 1, 0, 0, whether if it's 0 or 1, it seems to be random, like it's coming from the Ádám gate, but both of them are the same. They are always or either 0, 0 or 1, 1. You can think of it like if the first qubit becomes 0, then it doesn't change the 0, so it's 0, 0. If it becomes 1 here after Ádám, it will change the 0, so it will be 1, 1. This circuit calls the Bell circuit, and it's generating an entangled qubits. We can generate not just one, but if we repeat this CNOT to many qubits, we can generate many entangled qubits. And as you can see in the example, I didn't modify my code. For 10 shots, either if it's all of them 1 or all of them 0, but they are entangled, they are in the same state. Yeah. So I think most of us at first time think about it. Why is it is a big thing? It seems to be a simple copy of one qubit. We copy the 0. Of course, we put a Ádám before them, so it's either 0 or 1, but we just copy it. The fact is that we don't copy it. So let me show you how most of the people think about it. So we think about it like we have a pack of cards, we pick something out of it. It's an ace. So the ace is random, we pick out of a pack of cards, so it's random. Now we tore apart, put it in 2 envelopes, send one envelope to Alice, send another to Bob. They are far away from each other, but when they open the envelope, oh, I see the ace. What a big thing, but yeah, it's not a big thing. What about quantum computing is a really big thing, that the result of the envelope, what's inside, is not decided when we tore apart the pack, but only when we open the envelope. It's not decided at this time when we apply the Ádám gate. Even Albert Einstein was thinking that some kind of hidden variable is there, which determines what will be the result of this qubit, 1 and 2. Of course, both of them the same, but it should be determined by something. We don't know what, that's why we think it's random, but it's already determined. Later, or after Einstein's death, unfortunately, Bell showed it with the Bell's experiment, visible here, that it's truly random. The experiment is kind of easy to understand the logic behind. I was able to understand it in less than 1 hour, so now I don't try to explain it, but it's really it's smart, but it's hard to realize it, because you don't easily put qubits in entanglement and then travel it with a far distance. But with Bell's experiment, here you see the source. It's generating entangled photons in this case. There are 2 polarizers which are working in a random way. And then Alice and Bob measures the the qubit, the photon, the polarization of the photon, the qubit, and then these results are compared, and if it can be shown that if the result is whether it will be 1 or 0 is determined at source, there should be more coincidence than not. If it's determined only at measurement time, there should be the coincidence will be equal. And all of the experiments until now showed that the measurements are determined at, or not the measurements, the actual values of the qubits are determined at measurement time. So when we open the envelope. Until we don't open the envelope, they are truly random. There is no hidden variable which can be used to check out what will be, of course, the two same results. Okay, so yeah, that's kind of interesting, but what can we use it for? So here I show you two applications which works, but yeah, I talk about it a little bit. So the quantum teleportation and the superdense coding. When I hear the word teleportation, I always imagine myself as going into one door and stepping out in another universe. So it's kind of a cool thing. Also, when I hear about superdense coding, since we are coding, I usually think of some highly optimized code like you see there. What are they really in quantum domain? Everything starts with two qubits entangled. One is at Bob and another is at Alice. They apply gates, let's say usually a reverse Bell circuit, like here, Bob, and on the other side, Pauli, one input, one output gate. So superdense coding means that Alice can send 2 bits of information, let's say 0, 1, with 1 qubit. So that's why it's super dense. It's twice dense. So it sends 1 qubit, but the information is twice. Yeah, kind of seems to be a waste of resources to travel to the, let's say, to the moon with 2 entangled qubits to send 1 more bit of information. But it works. So it was proven and it works. The other thing is the teleportation, when we not teleport the particle itself, only its state. You can argue that if the state fully describes the particle, then it's kind of teleported. So if I teleport all of your atoms, or I don't know what, everything, then you are basically teleported, but it's kind of different if we just teleport 1 qubit. But these are the things which can go on the top of the newspapers and can create clickbait articles. So, and they are working. These are also the things which we are not using in a quantum computer, because we don't move far away each other, the qubits already inside the computer. So what can we really do with the quantum computer? The Grover's algorithm is one of the best, up to now, the best algorithms which can be used in several cases, and it gives us an advantage in terms of complexity of computing. It works best if we apply it for an unstructured search. So let's think of it like you have random numbers in a database and they are not sorted. the task is locate one of them. So you just trial and error. Index 1, is that number? No. If you have the answer no, you don't know, you have no more information, just that it's no. So you need to apply. You can apply from index 0 to, so you can apply one by one, you can try random, but at the end you can basically try each one until you find the last one is that. So that's why we say it's O(n) complexity. So this kind of sort can be done with Grover's algorithm in square root and complexity. We will see how this Grover's algorithm works. Grover's algorithm contains initially the n qubits, which we are interested in. Let's say A, B, C, the LS Becky Chris, this 0, 0, 0, and 1 qubit for flipping the phase. Then we put it into the superposition state. We don't entangle it, it's just putting in a superposition state. Then we need an oracle. That's basically how we design the Grover's algorithm, because other parts are mechanically there, the amplification and initial parts. But the real question is how we create an oracle. Oracle should be a function, but in quantum domain, so with quantum gates, which tells us whether the input is good or not. If it's good, it should say 1. If it's bad, it should say no. So if we can create this oracle, then we are good to go. We can, after the oracle, we have an amplification part, because it's just a mirror on the average. So we increase the probability of the good outcome, and we decrease the probability of bad outcome. And if we have just 2 qubits, we can apply it once and it will find the solution. If we have more qubits, we need to apply it more times, but it will find the good solution. Okay, so let's do it together. Let's go back to the code and check out step 2. You can, so you will have your step 1. Whatever you did here, it will remain yours. The checkout doesn't affect this. And let's first write a search algorithm in classic domain. So if I go back here, here is the hash message, the hash function, and I print out all of the, so I loop through all of the possible inputs. Here they are, and I put an X if the hash is 1111. So we are searching hash 1111. You see that there are 4 inputs which result in this 111 hash. So you can think of this algorithm, this for loop, as a brute force attack, but it's more funny if we do it in a random way. So let's say we import random from Python. So we know that it's not really random, but for now it will be good. We don't store any cryptographic information there. And we say counter. We want to count how many random trials and errors are necessary until we find this hash 111. So found equals false. And while not found, let's say increase the counter. Let's say we say input number equals random choice random element from this range, or choose a random element from this range. Let's say we format this input in as a binary string. And we fill it with zeros up to length 6. So here is our random input in format of 6 characters, 0 or 1. Let's say we print this input, so we want to have fun. What are the guesses? And if hash input equals 1111, then let's say we say found equals true. So it will break the loop, and that's it. And we print out hash found at step counter. Okay, let's hope we didn't create an unlimited loop. Search 1. Yeah, fun. So it's lottery time. You can run it many times. You can see that sometimes it's found at step 9, step 3, step 52. Oh my God. So raise your hand if somebody finds it at step 1. Step 1, me too. Yeah, so funny. It's kind of funny. In an average, you will find it at step 8. So you see that there are 4 of 64 is matching, so it's 1 to 16 chance. But of course, you are not always so unlucky that you find it at the 16th step. So in average, around 8. Okay, so let's do it in a grower's algorithm. You can open search tool. You can see that it's already done, and we had to create it. We had to create some. We had to define some kind of big gates, or seems to be like big gates, but don't be afraid. The CCC not gate is the same like the C not gate. It has only 3 control bits. So if the first 3 bits are going through and the 4 is flipping, only if 1 to 3 is 1. The same applies to CCC C not. They have 4 control bits, and the 5th one is the target. So they are implemented like this. The amplification is this one implemented for 4 bits. The quantum hash is the C0 chain, which we did together before. The reverse quantum hash is the quantum hash in reverse order, and here the find input creates the circuit. It negates the 7th bit. So we have 6 inputs, the 6 characters. The 7th bit is negated, yeah, like this, like this here. And we apply the Ádám gate. Then we apply the quantum hash, the CCC node on our targets, and because the first three bytes are, first 4 bytes are the hash, and the 7th is the phase change. Then we apply the reverse of it and apply the amplification. Then we run it. We grab the first measurement, first and last, because we have shot only one. And we just generating the bit string, first 6 qubits. So it's already done. You don't need to code there. And the same counter or similar counter which we see there, while not found, we try to find the input. We check with this classic function whether if it's 1111, and we say that hash found at step I don't know what. And if you change it, if you run it, you should see significantly less steps than in the first round. Okay, so who can go to step 6? I think nobody. Okay, so let's try it on a real device. If you have an AWS account, and if you have your AWS CLI prepared, then usually you just uncomment the local simulator and select a device from AWS, and you try to run it. Yeah, it's thinking. And it found for me at step 1. Like we can check here quantum tasks. Yeah, so this is that one. You can see the results in S3 bucket. If you download it, you can see the same or similar kind of results, like we were able to see it in. Yeah, you can see the measurements. Here is this. Here, that was the measurement, and some more metadata. So I did a trick here. This AWS device is just, as you see, it's another simulator. It's more powerful one than our computers. If we want to check it on a real device, yeah, you will be able to maybe to see the limitations of quantum computing. Here are all devices of AWS. From there, the first 3 are simulators, so not real quantum computers. Last 4 are offline. There are 2 available, the Harmony one and Area one. Harmony one still at Q35, which I posted this job there, so I'm still waiting to finish this job, but this device's performance is degraded. And Area 1 is 1814 still, so it will not perform any task. But if you go home and really want to run something on a real quantum computer, just If you put here a real quantum computer, it will complain about that it doesn't know some kind of gates, because you need to check which gates are available. I created a grover.py. It's the simplest possible grover. With 2 qubits, and it uses only gates which are available on this harmony. So it doesn't have even a CC knot, doesn't have a CZ. So we need to implement these quantum gates are somehow possible to build from another. So I built it for you for actual simulation. All of these gates are available at Harmony. So if you want to be one of the people who actually run something on real quantum computer, just try to run it on this quantum device. Okay, so questions. I hope you have more questions than when you came here. Otherwise, I am very sad, but who cares? Can I have a question? Is here somebody who actually perfect quantum scientist? Nobody, because I would have some questions to my presentation, but okay. Maybe somebody finds this video and I can ask him. If not, then thank you for joining.